recording the drive file. Your lecture and numerical section 2. Today, 8/4 2020. Okay, say. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, and a very good morning to everyone. So glad yeah to have another session with you guys. Okay, so up until now, please don't go out lah. Stay at home. Okay, and perhaps the pandemic of COVID-19 can be totally handled by our government soon. Okay, because if we need another extension, so it's quite difficult lah. Quite difficult for everyone. Okay, everyone. All right. So for today, okay. Before I move for today's content, so basically yesterday we finished our chapter number 3 on finite difference method. Okay, just to recall back finite difference method. So finite difference method. Okay, maybe I finish sharing to. Okay. Right. So yesterday, chapter number 3, finite difference method. Okay, so we have linear case, and we have also nonlinear. And both linear and nonlinear, basically we have the type of boundary condition. So your type of boundary condition, basically we have Dirichlet. We also have Neumann. So the last one should be Robin. Okay, so this is types of linear BVP maybe. Okay, nonlinear BVP. So your type of boundary condition for both cases, linear and nonlinear, should be Dirichlet, Neumann, and also Robin. Okay, and your main formula for finite difference, basically we have only two formula that you must remember. Okay, the first one should be yi prime, where we have 1 over 2h. So yi plus 1 minus yi minus 1. Okay. So the second one, we have another extension formula. Sorry, siapa yang. Okay, so you have 1 over h squared yi minus 1 minus 2 yi plus yi plus 1. Okay, this is the okay, this is the list of or the content that you studied in finite difference method chapter number 3. Okay, so for linear, so basically at the end are getting this system of ay equal to b, and then most of the time you can use that. Okay, so you can solve using inverse or Thomas.
Inverse
Why?
kalau 3 darab 3 je kan doktor?
Inverse for the case of 3 by 3 je. Kalau Thomas algorithm, okay, kita buat size more than 4 by 4 lah. Okay, 4 by 4. Size matrix A lebih besar daripada 4 kali 4. Lebih besar So, kalau untuk non-linear, so non-linear basically kita akan okay, kamu akan dapat system of vector valued function fy equals to 0. Okay, so daripada sini kamu akan tahulah sama ada kamu nak pakai Newton ataupun Broyden method yang kamu belajar dalam chapter berapa? Chapter 2. Okay, dalam sini nanti adalah Jacobian and so on lah. Jacobian dan seterusnya. Okay, so this is basically what you will have in your, not you will have, but this is what you have in your chapter number 2. So, alright, is it okay? Okay. So now we move to the another sharing. So how can I? Okay. So this is our chapter number 4. Okay. So I would like to remind you total chapter in this numerical methods 2 is actually up to chapter number 6. Up to chapter number 6. So the fourth chapter should be shooting method. Okay, basically shooting method is the alternative method. Okay, you can see here alternative method, alternative numerical method, where we want to solve any boundary value problem. Okay, so just alternative. So even you can use finite difference method to solve boundary value problem, or maybe you can use shooting method. So same goes to our third chapter. So since we are solving boundary value problems, so we are having actually 3 different boundary condition. Once again, Dirichlet boundary condition, Neumann, and also the last one, Robin's boundary condition. Okay. All right. So okay, for the linear case, okay, for the linear case of boundary value problem, so this one. So for the linear case of boundary value problem, shooting method basically we apply this method by introducing 2 different initial value problem. This one. Okay. So you have your problem of boundary value and then you introduce new 2 IVP. So it means that we have IVP1 and also the second one IVP2. So each IVP will brings their own not formula but equation. But basically that equation is referring to your original boundary value problem. So later I will talk about this one later in detail. Okay, just here if you look at here, the specific form of the IVP is basically okay, right? Since we are having these 2 IVP, so we have 2 IVP means that when we solve these 2 IVP, we are getting solution from these 2. Okay, let's say the first IVP you are solving in U notation, the second one you are solving the V notation, V solution, you are getting solution of V for the second one. So by adding these 2 solution of U and V, U from IVP1, V from IVP2, So you combine these two using linear combination, then we can get the solution of our boundary value problem. So we are using linear combination. Okay, so go back to your linear combination. You add this two solution, but must remember the second solution must multiply by another variable, another parameter. Okay, later we'll explain. Okay, so that is the idea when we are solving boundary value problem for linear case. Okay, for non-linear boundary value problem, so this leads to the iteration process. Okay, you will have another iteration process, which is now your iteration process, you just able to solve using secant or Newton's. Okay, means that secant is the new method you will study here, and same goes to Newton's method here, because this Newton's method bear in your mind not similar as Newton's method in your chapter 2. Okay, Newton's method in your chapter 2, basically you are solving Fy equal to 0. But here, okay, ada okay, ada algorithm, but they are using same names of the method, which is still Newton. But this is different with your previous chapter 2. Okay. Okay, now we go to the linear case first. Okay. Once again, since this is boundary value problem, okay, so boundary value problem means that your condition should be involve at least two conditions, and the first condition should be with respect to your okay, left hand or x naught, and the second condition should be on your right hand, which is x n lah. Okay, so this is example for the Dirichlet lah. Same goes to for your Neumann. Okay, they will give you condition on your x naught, and also for Robin also you have x n and also s n. Okay, this is when we are talking about boundary value problem. So second order means that y double prime must exist. This term must appear in your equation. How about y prime? How about y? Yeah, this is not necessarily must exist here. Okay, but you need this y double prime because this is second order. Okay, so if we look at here for linear case, so we have y, which is your dependent variable. Okay, its derivative y prime and also y double prime. So must be power of 1. And their coefficient for y is q, means that any function with respect to your x or generally independent variable. So the coefficient here px, and the coefficient here is just 1, here 1. And how about Rx? Okay, this is the part that will identify whether you are having homogeneous or non-homogeneous linear differential equation. Okay, so if this Rx is equal to 0, means that there is no terms, okay, extra term without y, okay, because there is no y. Okay, so you are not having this Rx, means that you are getting homogeneous. If this Rx is not equal to 0, means that, for example, okay, you have this one and then plus 2, or maybe plus sine x. So means that Rx is not equal to 0, we are having non-homogeneous linear differential equation. Okay, so this is regarding to the equation. Okay, and then for first boundary condition that we discuss here for the Dirichlet. So once again, okay, for the Dirichlet, you are having y x naught and y x n. There is no prime here. Okay, means that this is already the solution for x naught. Okay, the value of y is alpha, in general alpha, and also solution of y for your xn is actually beta. Okay, means that you are not need to find solution y x naught and y x n anymore. So you need to find y x1, y x2, y x3 until y xn minus 1, not y xn, because this is already solution. So generally we are using notation here alpha and beta. Okay, beta because this is very important. Okay, because some of the later term here they are using alpha and also. Alright, now Okay, this is regarding to homogeneous, where Rx. So go for the algorithm. Okay, step by step that you need to do when you want to solve linear second order for the Dirichlet boundary condition. Okay, look at here. This is our first initial value problem. Okay, previously I mentioned here we have to reduce or introduce your BVP to two different IVP. So this is your IVP1, this is your IVP2. Okay, so for IVP1, basically we are just copying our boundary value problem here, 4.1 here, equation 4.1. We just copy by substituting y notation into u. Now we are having u instead of y double prime, here u prime instead of y prime, and here u. Okay, we are letting y as u. Okay, and Rx remain here. Instead, just similar exactly as your original BVP. Okay, so why you are changing notation y into u for IBP1? Because you might be confused later. If you stick using y here, y and y, this is possible. Okay, the reason why we are changing the notation because we want to avoid any confusion later. Because later, after this, you will solve this IBP1. At the end, you are getting solution of u. If you are solving this IBP1 using notation y, 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 later you are getting solution y, 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 y. So you might be confused. Is it solution that you are getting from IBP1 is actually our solution for equation 4.1? What is annotated? Okay, so you might be confused because this solution y you are getting from IBP1. You are still not solving for BVP. Okay, that's why we change the notation. Alright? Okay, so your condition now. Okay, since this is initial value problem, means that your condition should be using initial value or just one value of x. Okay, since you are having second order, means that you need two condition. But these two condition must with respect to just one value of x, which is here we are using just x naught and x naught. Okay, so we still have two condition, but with respect to x naught both. This one u x naught, this one u prime x naught. That is initial value problem. Okay, so look at here, u x naught. Okay, u x naught. The value here must be alpha. Okay, means that whatever alpha appear in this 4.2 for your y x naught. Okay, y x naught. Whatever value here, is it this maybe this is 2, maybe this is 4, maybe this is 10 minus 1. Okay, any values, so you should put the same value here for alpha. If alpha here is 2, so here should be 2. Alpha here is minus 1, here should be minus 1. Understand? Okay, this is copying alpha here. How about this u prime x naught? This value of 0 basically fixed. Do not change the value of 0 here. Okay, this is fixed 0. For all the time when you are using shooting method, you want to solve for linear case of boundary value problem. So you reduce into IVP1. Here u prime always 0. Never change the value. So means that you cannot put this one another value. Let's say 1, 2, cannot. Must be 0 here. But this one depends on the value. Okay, understand? Okay, this is regarding to your IVP1. Okay, once again, this is x naught. In other words, your left end here. Okay, if x naught is 0, so you put here 0 and 0. If this is 1, you put here 1 and 1. Okay, depends on the value here lah. Alright. Okay, now Okay, I proceed to the IVP2. Okay, we go to the second initial value problem. So for the second initial value problem, now, so your Y notation we change to V. Why we are not using U? Yeah, to avoid another confusion. Because if you are solving U here, you might confuse. Is it this U is similar as this? Because after this, you need another value which is U later here. Here. So if you are using same notation U here, so it's quite messy lah. So that's why we use different or another variable, another symbol which is V for IVP2. But here, look at closely. Here in this IVP2, your Rx disappear. There is no Rx here. Means that if your Rx here is 2x, for example. So for IVP1, 2x appear here. But for IVP2, there is no term of 2x. Okay. How about P? Yeah, this is the main just Rx. Just Rx. Okay. Remember, IVP1 we have Rx, IVP2 we don't have any Rx for your second order equation. Okay. Then okay, similar as IVP1, this is initial value problem. You need two conditions because of second order with respect to just one value of x naught. So V x naught equal to 0, V prime x naught equal to 1. So once again, now here 0 and 1 are fixed value. Okay, V x naught must be 0. V prime x naught must be 1. You cannot shuffle the position. For example, you want to put 1 here. Cannot. This must be 0. Okay. You want to put 0 here. Cannot. This must be 1. Okay. That is the condition for IVP lah. IVP2, sorry. So when you are introducing these two IVP, so later we want to solve. Okay. So when we want to solve this IVP, so basically this is back to your first chapter of solving any initial value problem. Okay. And even you have the system of initial value problem, the last part of your first chapter. So this is, you will reduce both IVP. Okay, when you want to solve, you will reduce them into system of first order. Okay, means that here we have second order. So you have system of first order. Okay, later maybe you can refer to your notes. Okay, or you can wait for our example. Okay, so we are getting system of first order. Then we are solving that system. Okay, when we are solving that system of first order, go back to your first chapter. Okay, possible what you call it, possible method to solve this IVP lah. Okay, so from your single step method, maybe you can use Taylor series expansion. Maybe you can use Euler's method. You can use midpoint, Panchkata, second order or fourth order, Q, all those single step methods. Okay, available lah. You can use software. But normally during the exam, we will give the specific method that you need to solve, you need to use to solve this both IVPs. Okay, we'll give you the specific method. Okay, right. Okay, once you solve IBP1 and then you solve IBP2, means that you are getting solution for you. Maybe you are having UX0, UX1, UX2 until UXN. Same goes to IBP2. You are getting solution for VX0, VX1, VX2, or VXN lah, until VXN. Okay. So now we are using that solution from U and V. Okay. So if you still remember linear combination. So from both solution, basically, so we are having the solution for our boundary value problem here. Okay, this is y. So it's actually equal to the linear combination between these two solution of IDPs. So first you have Ux, and then the second one you have the solution for Bx from second IDP. As I mentioned, the second one, the latter, okay, you will need to multiply by another parameter to differentiate between these two. So, and that parameter basically just a constant. You can use any symbol here basically. You can use a symbol of A, B, and even you can put your name. For example, Hakim. You put Hakim here. It's up to you. Okay. But here, since we are using shooting method, yeah, give credit lah to shooting method. That's why we are using S symbol to represent the parameter. Okay, right. Okay, up to equation 4.6. Any question? Any question you want to ask? Open for question. Any question? Ada. Okay, boleh proceed. Faham ke ni? Ha?
Faham.
Ha? Saya pun tak faham saya punya English ni. Aduh. Okay, right. Okay. So look at here. Okay. Why this equation 4.6 is actually it can be used lah to represent the solution of our BPT. Okay, basically this equation of 4.6 satisfy equation 4.1. Okay, how to check whether this 4.6 satisfy 4.1? So you may substitute lah. Okay, because here 4.1 we have y double prime, y prime, y. So this y you can substitute into this y. Here. Okay, 4.6 you can substitute. How about y prime? So you differentiate this one, y prime. And then later you substitute here, y prime. And how about y second, y double prime? So you differentiate once again, y double prime, and then you substitute here. And make sure left hand side and right hand side should be equal. If left hand side and right hand side equal, means that this solution y or equation 4.6 actually satisfy 4.1. Okay, right. So and this solution also satisfy your initial condition. Okay, or your boundary condition. Here, the first boundary condition. Y x naught alpha. So simple. Okay, let's say this x you substitute by x naught. Means that here become x naught. Here also become x naught. Am I right? Okay. So now here y x naught. What is the value of y x naught? Should be alpha. Okay. You put alpha here. You put alpha here. So left hand side now become alpha. So right hand side. So u x naught. What is the value of u x naught? Here from IVP1. Also alpha. You put alpha. Okay. And what is the value of Vx naught? Vx naught is 0. Means that you plus S multiply 0. Yeah. You are getting 0 here. Now alpha on the left equal to alpha on the right plus 0. So means that both sides are equal. So since both sides are equal, once again, they satisfy the condition. Okay. All right. Okay, that is regarding to your first boundary condition. Okay, how about the second boundary condition? Okay, which is your yxn equal to beta. So we will use this yxn, okay, to determine the value of s. Because initially we don't have any values of s. How to identify, how to get the value of this s? So from your second boundary condition. Okay, what is the process? Okay, look at here. So your second boundary condition yxn means that now you substitute this one by xn. Okay, so this is xn, this is xn. I'm sorry, this is typo, should be xn. Okay, it's not x0 but xn. So yxn, so we have usn plus sbsn. So for y at n, yes, you can substitute by this beta here. Okay. And how about u at n? Okay, u at n, you can get the value from your IVP1 because later you will get solution for u at x equal to x. You substitute. How about v at n from IVP2? So you will solve this IVP2. At the end, you are getting solution for v at n. Use that value, substitute here. Means that now we have value of y at n, which is beta, u at n from your IVP1, v at n from your IVP2. Then you might find what is the value of s. Okay, you rearrange lah, and then you are getting equation 4.7. Okay, this is from your second boundary condition, IVP1, IVP. Okay, this is for the case if your v at n is not 0. Okay, if this is not 0. How about if this is equal to 0? So if v at n equal to 0, obviously this is eliminated. There is no s term. Okay, if there is no s term, basically y is equal to, okay, here, y is equal to just ux without this term, because v at n is equal to 0. You cannot get s. So we are saying that basically we are having y at n equal to just usn. Okay. Okay, right. So this is just their here we write the solution, substitute this s inside 4.6s here. So you are getting equation 4.8. Okay, right. So for the first part, any question you want to ask? You can understand or not?
Yes.
Okay, good.
Doktor,
Yeah.
yang tersalah tulis tadi tu YX not lah.
Yeah, this one. Yang ni patutnya YSN. This is supposed to be YSN. Sorry.
Okay.
Okay. This YSN Ini kat atas ni dah tulis substitute x equal to xn. JSN. Typo. Yeah. Okay, any other question? May I proceed?
Ada, bersih-bersih.
Okay, mantap. Okay, now okay, look at the example available here. So we have 4.1 and 4.5. So we have 4.1 Euler, 4.2 midpoint, Yun. This is just algorithm. Oh, RK2, sorry, RK2, and the last one RK4. So should be, this is just your warm up lah, warm up example. So maybe Euler should be, okay, Euler is the easiest method. So for your warm up example, so we are solving example 4.1. Okay, now, okay, equation, okay, sorry, example 4.1. So I will go to another, okay, right. Go back to here. Okay, example 4.1. Okay, the question should be y double prime plus xy prime minus 3y equal to 4.2x. So your condition should be y0, 1. So y and 1 is equal to 1. So yes, your h 0.25. Okay, so here, okay, so here there is no prime. No prime means that this is Dirichlet. This is Dirichlet. So here, this is your alpha. This is your beta. Right? Okay? Okay, right. So this is your Rx. Okay, careful with your Rx. Why? Because our second IVP, we don't have any Rx side. We are not considered Rx. Okay. Now, okay, let's say, okay, from this boundary value problem, so maybe you can get your x not equal to 0. So this is your, okay, this is your x1, 2.25, x2, 5, 3, 0.75, and x4 here should be 1. Okay, from your boundary condition, we know that y
Doktor, yang alpha tu sama dengan kosong ke satu?
1, 1. Sorry, this is where is it? Okay, this is 0. Sorry. Alright, so y naught should be equal to 0 lah. Y naught 0. Y1 we don't know. Y2 also no solution. You need to find Y3, and for Y4 this is means that for Y you need to calculate for I1, 2, 3. This is for Y. Alright, okay. Alright. Any question? Understand up to here?
Okay, understand.
Okay, ni adalah usual ni lah, usual step lah. Every time you got your question, you should. Okay. What's time now? Okay, right. Okay, right. So now we proceed to our. Okay, so maybe okay, right. Yeah. So you may start to introduce your IVP1. Okay, IVP1. So IVP1. So now we are letting U as Y. So means that your IVP1 should be like okay. So U double prime equal to, so I put plus xy here. This one I put these two terms I put on your right side. Okay. So means that we are having minus x u prime plus 3 u plus 4.2x. Okay, and your u x naught. What is your x naught? This is your x naught. This is your x naught. Okay, your x naught should be 0 equal to your alpha. What is the value of your alpha? 0. Okay, so u prime x naught 0. So the value should be this is fixed. This is fixed value. Okay, always 0. Always 0. This one can be changed if your alpha here is not 0. Maybe alpha here 1, so here it should be 1. Okay, understand? After this, any question? Ada nak tanya?
Okay.
Okay, right. Okay, now, so we solve this IVP1 first. Okay, when we want to solve, so we reduce to system of reduce into system of reduce into system of of first order. Okay, refer 1. So means that here we let u prime equals to, for example, maybe z. So z prime is actually equal to u double prime lah. So which is u double prime is negative x, and your u prime here, okay, this is your z prime z prime equal to u, okay, so u prime here now becomes z. Okay, now you change here to z. Okay, plus how about u remain as u. Okay, we just change u prime, it's not u remain as u. Okay, plus, and also x remain as x, and the condition for u we need condition u, for z we need condition for z. So what is the value that we should put here? Yeah, from here, this is 0, this is 0. So u0 similar as here, so means that equal to 0. Okay, z0, what is z0? Z0 means that u prime 0. Where is your u prime 0? Here, from the second,
Zero.
okay, second condition. Alright, so now, okay, okay, look at the question. They ask you, okay, they ask you use Euler's method to solve the corresponding initial value problem. So this is your initial value problem. So this is your initial value problem. So it means that to solve this initial value problem, you need to use Euler's method. Okay, Euler's method. Alright. So if we are using Euler's method, okay, before that, we write, okay, x naught 0, x1 0.25. Okay, this is just follow your boundary value problem h. H for your boundary value problem. If your boundary value problem, their h is 0.2, so all IVP, their h must be 0.2. Okay, so here means that this is u naught. What is u naught? Means that, okay, u naught is actually u x naught, or in other words, u in bracket 0. So this is your u in bracket 0. So means that here u naught should be 0. Same goes to your z naught. Your z naught here, okay, z x naught equal to 0 is actually z equal. So how about u1? z1, u2, z2, u3, z3, u4. How about z4? Do we need to calculate z4? Do we need to calculate z4?
No.
Oh,
Not need here because we just need up
Tiga
to
X5.
uxn. If you still remember when you need to calculate s. So n here is actually, this is ux4. Okay, so not necessary to calculate this z4. Okay, how about z3? Yes, you have to calculate z3 because if you don't have z3, you cannot calculate u4. Okay, so means that here for your k, depends. So now Euler's method. So ui plus 1 is equal to ui. Okay, so ui u plus, sorry ada yang saya terpaksa mute sebab apa, ganggu siaran. H, let's say this is f xi ui zi, and another one, sorry, zi plus 1 equal to zi plus h g x I u I. So since we are using this formula I plus 1, so look at here. So you want to find first value here u1. How to get u1? So means that we have to plug in I0, then we are getting 1, u1. Means that I start from 0, 1, 2, 3. Why 3? Because if we put I3, we are getting u4. So this is your u4. Do we need to put 4? No, because we are not looking for u5. Okay, we are not looking u5 here. All right. So how about our F here? How about our G here? So from your this is your F X I F X U Z. Okay, this is your G. Okay, this is your G X U Z. Okay, after this, if I mention, okay, when we start to calculate, we start to solve this identity. When I call for function f, remember, f is just z. And when I mention g function t means that is minus z plus 3u plus 4.2x. Okay, clear? Alright. Okay, so now we start to solve. Okay, so let's say I'm inserting betul sekejap so where do we need to put okay, right. So this is I, this is xi, this is ui, this is zi, your f, this is your I plus 1, this is your g, this is your okay, right. So now, so this is I, xi, this is your ui, this is your zi, this is your sorry, f, xi, ui, zi. So this is your ui plus 1, your g, I, ui, zi. This is your zi plus 1. Boleh nampak tak table ni? Boleh eh?
Boleh.
Right. Yeah, alright, so now you start I. Okay. So we know that I 0, 1, 2, 3. So you put 0 here. 1. And then look at your x0, x1, x2, x3 because this is xi. When I0, x0. So x0 should be 0. So x1 should be 0.25. x2 should be 0.5. x3 should be 0.75. Okay, now UI. So this is I0. So U0. Where's our U0? Here. This is U0. This is Z0. Okay. Right. So this is your U0. This is your Z0. So means that U0 is 0. Z0 should be 0. Alright. Now we start to calculate. Okay. F. Still remember F is equal to Z. Put here Z. Okay. So this is optional lah. Optional. So means that F basically just copy the value here. So this is your Z. So should be this is also 0. Okay, once again, how to get the Z from your this part. This is your F, this is your G. Okay, next, calculate for your U. Okay, U1. So U1 equal to U0. Okay, this is your U0 0. H 0.25. Okay, H 0.25. Okay, and F is 0. So means that 0 plus 0. So here still we are getting 0. How about G? G. G, okay, maybe I need to write G. G is equal to negative xz plus 3 4.2. Okay, this is your G. So X, your X is 0. So means that here becomes 0. Your U also 0. At 0 means that G also 0. Okay. So now calculate Z. So since this is 0, here multiply H also 0. So now look at your Z naught. Z naught is also 0. So that here should be also 0. Okay, once you are getting all zeros here, don't quite what we call it, curious lah, because later the value should be come out lah, okay, other than 0. So just proceed. So now, so we proceed to I1. I1, so U1, so U1, this is your U1. Means that just copy back your U here. And also this is your Z1. Z1 is 0, so you write here 0. Okay. Once again, F. F equal to Z, just copy. If this is 0, then 0. Is it U1 equal to 0? Okay, depends. Look at this formula. Your F0, yes, this becomes 0. Your U, okay, this is I1. So U1. U1 is 0. So since 0 plus 0, another 0. Another 0. Yeah, is it our G0? I don't think so, because look at here. Okay, this is X. Yeah, X we have the value 0.25. But Z0, so this is 0. U also remains 0, but not for this one. Please calculate, because your X is 0.25 now. So your G should be not 0. So 4.2 multiply 0.25. What is the value? What is the value here?
1.05.
1.05.
5. Okay, then proceed with your Zi plus 1 means that Zi here 0 plus Hg. So H is 0.25, G is 1.05. Berapa nilai?
0.625.
0.2625.
25.
Right. So now this is your U2, this is your Z2. So you copy here U2, 0, Z2 is 0.26. Okay, copy from here. Alright, now once again F is just similar as Z, so you just copy 0. Now is it your UI is also 0? I don't think this is 0. Because this is not 0. So 0.2625 multiply dengan 0.25, isn't it? Berapa jawapan dia?
0.0656.
0.0656.
56.
Proceed with your G. So better you put this formula lah in your calculator. You key in this formula and then you just put the value here. X. This is U. This is Z. This is quite easy lah. Okay, what is the value here, G?
1.96.
1.
96.
9688.
Okay, 1.9688. And your Z? 0.7547.
7547.
Okay, so this is 0.0656. This is 0.7547 and it should be similar. So what is the value for your U4 here?
0.2543.
0.254.
43.
Okay, 3. So look at here. Okay, our previous diagram, we are calculating until U4. Means that we are not finding Z4. So this is Z4 supposedly. So these two part just ignore. Okay, not necessary lah. Okay, until this solution, IVP1, any question you want to ask? Any question you want to ask? Okay, step by step here, example 5.1 until I get the solution. Is it okay? Boleh?
Boleh.
Boleh.
Semua dapat jawapan yang sama?
Dapat.
Kalau ada dapat jawapan yang berbeza, bagi tahu Okay, now we proceed to IVP2. Okay, IVP2. So go back to your IVP2. So now kita tulis let Y. Okay, daripada yang tu kita tulis sebagai V pula. Okay, tadi untuk your first IVP, we let Y as U. Now for second IVP, Y as V. So now we are writing our new IVP. So V double prime. Okay, negative X V prime plus 3 V, isn't it? Yeah. Okay. Okay, how about Rx? No Rx here. Okay, no Rx. What is your Rx? This part. This is your Rx. So for second IVP, do not write this term. Okay, only these three. So you bring these two to the right, so minus x v prime plus 3v because we let y as v. Okay, so now your condition should be vx0 is 0, always 0, and okay, the second v prime x0, okay, this is always 1. So once again, these two value fixed value. Okay, for all the problems here, okay, for all boundary value problem, when you want to use shooting method, when you reduce into IVP1 and IVP2, okay, IVP2, here, the value here always 0, and this one always 1. Okay, alright, so now, okay, we reduce once again, reduce to first order system, so we let, okay, just now, okay, V prime lah. V prime, so just now we are using Z, maybe here W. So W prime is equal to V double prime, which is negative X. So V prime should be W plus 3V. Okay, so how about the condition? So for V prime, we should give V. For W prime, we should give W. And the value here from these two, so 0 and 1. Okay. So since we need to use also Euler's method because the question said that solve the corresponding IVPs using Euler. So let's say, okay, instead of F, because we use F here, we use G here in our first IVP. Maybe here we are using different notation. So maybe this is just what you want to use. Okay, maybe just P X, your independent variable, and V, your first dependent variable, and your W. So this one should be your, this is your P and Q lah. X, V. Okay, if you have any question, just you ask lah. Yeah, disrupt me, don't worry. So X0, once again 0, X1 0.25, X2 0.5, 3 0.75, 4 is 1, difference here 0.8. So okay, we have V not now, V equal to 0, W not equal to 1, but not for V1, W1, V2, W2, V3, W3, V4, W4. Do we need to calculate W4?
No.
Not necessarily here. Sebab apa? Sebab later when we need to calculate, we need Vxn. Sorry, Vxn, which is Vx4. Okay, up to V4 only. Okay, same as our IVP one. So now, okay, once again write the formula. So since we are solving for Vi plus 1 equal to Vi plus H. So we are using PP lah. X VW. So Wi plus 1 equal to Wi plus HQ. Sorry, XI, VI, WI. I, VI. Okay, your I. Okay, once again, I equal to 0, 1, 2. Just a moment, eh. So, and alright. Okay, up to here. Any question?
Doktor,
Yes.
Ada.
doktor saya ada.
Tanya. Sila.
Kita memang kena solve untuk dua-dua IVP
Ya, saya betul.
Okay.
Sedihnya bunyi.
Kenapa sedih? Panjang kan? Okay, so draw your table. Okay, once again, 1, 2, 3, 4, 5, 6, 7, 8. 8 columns, 5 rows. So because your I start from 0, 1, 2, and 3. So Xi once again is not 0, 0 0.25, 0 0.5, and 0 0.75. Your V naught should be 0 and W naught is 1. So, okay. Okay, so W is always your P equal to W. So once again, this is just similar. So you put 1 lah. So now calculate your Vi plus 1. What is your Vi plus 1? V2. Sorry, V1. Sorry.
0.25.
0.25. How about Q? W, okay, X0, V0. So Q should be 0, isn't it?
Yes.
And then since Q 0, so W 1, so I plus 1 here should be 1. Okay, so copy these two values, V and mu W, so you put it here 0.25 and here is 1. Once again, P become 1 because similar as. Okay, now calculate for Vi plus 1. What is the value of V2? Okay, this is V1. So here now we are calculating for V2. Berapa nilai dia? 0.
0.5.
0.5. PQ
0.5.
0.5. W saya collect apa nilai je ni. Saya collect data je. Pastikan semua buat Okay, make sure everyone try to solve this example Okay, what is W2? One point
125.
1.125.
125. So here become 0.5. Here become 1.125. Here also 1.1. Okay, proceed. Get your V3.
Kosong point 78.123. Gitu.
0 point
7813.
Alright, okay, 7813, okay. Q berapa? Kosong mungkin. 0 point
9375.
9375. Okay, nice. Okay. And your answer last?
1.3594.
Okay, 3594. Okay. So this is 7813. 1.9.
3.
Same here. Right. Last V4. What is your V4?
1.1299.
1299?
1.1299.
1212, isn't it?
Yeah, 1212.
1212. Okay, so means that here, okay, once again, we are not calculating this one. Just leave it blank also possible. Okay, right. So, semua dapat jawapan yang sama?
Sama.
Tak dapat.
Tak dapat?
Dapat.
Dapat.
Okay, so this is your, okay, this is your VX4 or V4. Okay, another one. This is your UX4 or, okay. Why I highlight these two? Because we will use these two values to calculate for your S. Okay, now you want to calculate your S. S equal to okay, y x4 minus u x4 divided by v x4. Okay, so means that y x4 basically is from your boundary condition, your original problem BBP, second boundary condition, which is beta. What is the value of beta? Beta, berapa beta? Okay, beta 1 here. Okay, beta is 1. So substitute 1. So you get here 1 minus, okay, u x4 just now 0.2543.
3.
Okay, point. Divide by 1.2, sorry, 1212. Okay, what is the value here? Berapa nilai dia?
0.6651.
Okay, 0.6651. Okay, so this is your S value. So we will use this S value, okay, into our linear combination solution. So therefore, sorry, using black. Okay, so we have therefore, okay, we know that y, okay, y xi equal to u xi plus your s v xi. In other words, your s should be ui, okay, ui plus 0.6651 vi. So now, okay, how to get the value? So go back. Okay, so this is your solution yi. But is it we need to find all I 0 until 4? No. Okay, look at back. This is your original. This one. Okay, this is what we need. Saya pun tak tahu ni kalau apa. So this is the only I that we need to consider when we want to find the values of solution y. Okay. So now I equal to 1 until 3. So for I equal to 1, so means that y1 equal to u1 plus 0.6651 v1. So what is the value of u1? Where is the value of u1 from your? This is your u1. Okay. This is u1. This is u2. This is u. Okay. Same goes to this is your v1, v2, v2. Okay. So u1 is 0. Okay, go back. Where is it? Where is it? Okay, u1 is 0. 6651. v1 is
0.25.
0.25.
what is the answer?
0.1663.
0.163.
63. Okay. Okay, I equal to
2.
Okay, just a moment. Okay, right. So you continue for I2 and I3 lah. So Y2 is actually, what is the value of U2? U2 is 0, isn't it?
0, yes,
6651, and V2?
0.5,
Okay, and your answer?
0.33.
0.3326,
Okay, continue for I3. Y3.
0.006.
0 point
0656.
0656,
multiply 0 point.
7813.
783,
Your answer?
0.5852.
Alright. So this is the final solution. Okay. So once again, I would like to repeat. Okay. So when you are getting any problem, any boundary value problem, when they ask you, okay, they ask you solve using shooting method, just general shooting method, but they will give you another hint, which is what method that you need to use to solve the initial value problems, IVP1 and IVP2. So they okay, if this is shooting method, this is your technique. Must exist IVP1, IVP2. And then they will guide you use another method to solve the IVPs. So for example, in this particular example, so we have Euler formula lah. So you need to use the correct formula for solving IVP1, IVP2. Okay. So okay, right. So for Dirichlet, once again, there is no prime here. Okay, this is Dirichlet. Automatically, you know this is alpha, this is beta. Okay, why you need to know the values here? So basically, if you don't want to remember this one, also possible, but you have to be careful. Why? Because when we are introducing our IP, here is always equal to alpha. If you are not memorizing this is actually alpha, it's okay. You must remember when you want to put the value of u naught here, must take the value of y for your x naught. Okay, it's not always here 0. If your x naught sometimes, okay, x naught start from 1, so here will be 1. So your x naught, okay, is 1. So here will be 1. Okay, this is not always all the time 0. No. Okay, so okay, right. So this will be the second boundary condition. You will use the value here when you want to identify S value, okay, parameter of your shooting. Okay, so first, okay, you identify your Y. Here, I would like to remind you there is no mark for this. If you want to skip, it's okay. Okay, just this is as your guideline. So introduce your IVP1. So IVP1, so consider all exactly similar term here. Okay. If, for example, if this Rx is 0, means that we don't have any Rx here. We don't have this 4.2x. Same goes to your second IVP. You don't have Rx. It's okay. Okay, don't worry. Okay. Is it the solution we are getting same values for all? No. Okay, because even though we don't have Rx here, so here also automatically don't have Rx because this is the concept of IVP2, no Rx. Okay, no Rx. So no Rx. No. Okay. So even though the equation is quite similar, but because of the condition 0 and 1 for IBP2, but this is 0 and 0 or alpha and 0. Don't worry, because this condition, your solution might give different values later, okay? Even though your Rx is 0. Right, so you introduce IBP1 carefully. This is fixed value 0, and then reduce into system of first order. You are getting this system, and then you solve using mention the correct formula lah. They ask you to use order, use order. They ask you use midpoint, use midpoint. Okay, and then you solve the IBP. You may just draw the table. Okay, this is optional. Okay, this is optional. Okay, how your table looks like, this is just optional. Okay, but for me, I think this is the most appropriate lah, because when you want to calculate g, x, u, and z here, you need all three values here. You don't have the values here, maybe it's quite messy lah when you need to find another place for the value of x and u and z. Okay, so for IBP2, once again, no Rx. So the value here for your condition, initial condition here fixed. So v not 0, v prime not, v prime x not is 1. And then this is optional. If you want to stick using f and g is okay. Okay, let's say because I want to use a different notation. So you solve until you get this one. Okay, you are not calculating for W4 up to V4 only. Okay, and then once you solve IVP1 and IVP2, you might get the value of your S using this formula. How to remember this formula? Just you remember y equal to u plus s. Okay, and then you put I equal to 4, then you might get your S. Can we consider, okay, in order to find S, okay, my question is, if we want to find S, can we use x3 here instead of x4, for example? Any question? Any question? Any answer? My question is, can we use x3, for example, x3, 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 to find the values of S? Someone want to try? You hear me, isn't it?
Kita kena tengok FN dia kan.
Tapi tak ada nilai Y3.
Okay, good. So basically cannot, okay, cannot use yx3, cannot use yx2, cannot use yx1. Why? Because we don't have any information, any values of yx3, yx2, yx1 from your here. Because we just have the value y0, which is yx0, and we have yxn, yx4. There is no yx3, yx2, yx1 here. So that's why when you want to calculate this S, only we use ys, because this can be obtained from your second boundary condition of BVP, okay, which is 1 lah. Okay, so US4 you can get from IBB1, VS4 from IBB2. So once you get your S, substitute lah into your general linear combination of Y here. Okay, then you get this one. Now you decide which I that you need to consider from your first part. This one. Okay, so I is just for 1, 2, 3. So you consider lah just 1, 2, 3. How about if you want to put I0 and also I4? It's up to you. at the end you are just getting same values. But here basically not necessary lah. I0 and I 1, 2, 3 only. Okay, understand? Any question?
Understand, sir.
Okay, so where is it? Stop the recording, but I cannot resume. Okay, okay, tak apa. Okay, so can we proceed? Just to fill another 15 more minutes. Boleh? Boleh sambung? Okay, so saya alamak. Okay, saya dah tahu. Kamu boleh nampak tak sekarang saya buka PDF?
Tak. Tak
Kamu masih lagi
nampak.
kamu nampak saya punya EndNote je? OneNote. Okay, alamak. Ya, tengah hang lah. Hang. Siapa?
So dia
Siapa?
soal apa akut?
Bukan. They are asking for the folder. Folder. Okay, folder. Just a moment. Okay. Alright, so I start another recording. So I start sharing for previous screen. So we move to the other screen of. Okay, now you can see this PDF.
Yes.
Okay, good. Okay, right. Okay, now just maybe we can cover up for the theory only. Alright, so now for the second type of boundary condition, so we have this what we call it as Neumann. Okay, Neumann boundary condition. So if you still remember, basically Neumann is not just this condition 4.9, because we also can get another form of Neumann, which is y prime x naught and also y prime x n. And even we can get y prime x naught and just y x n. Okay, so for this particular example, okay, we just focus initially for this only type of Neumann boundary condition, which is y x naught without prime and y x n with prime. Okay, how about the other two? That one later. Alright, so now, okay, if you can see here, okay, so basically we are using just similar solution linear combination from equation 4.6, which is in your Dirichlet boundary condition. So once again, if we are using this one, okay, this solution satisfy our second order differential equation 4.1, and also initial condition y x naught. That's why for Neumann, we just consider this y x naught because we want to use that solution y equal to, where is it? Okay, equation 4.6, y equal to u plus s. Okay, that's the reason why we need to focus with this one. Okay, all right. So now we have this type of Neumann boundary condition. So, okay, the process is just similar. You will reduce into two different IVPs, IVP1 and also IVP2, similar as what you have in your Dirichlet boundary condition. Okay, same consideration, IVP1 with Rx, IVP2 without Rx. Okay, the values here should be similar, Ux0 should be equal to alpha. Okay, from your first boundary condition, okay, u prime should be equal to 0, v x naught 0, v prime equal to 1, okay, same conditions, and then you solve until you get the solution of IVP1 and IVP2. How about now? How about your S, okay, when we need to find S? So we cannot use our previous formula here. This one, equation 4.7. You cannot use 4.7. Why? Because 4.7, they are using yxn. Yes, in Dirichlet, we can get what is our values of yxn from here. But since in our Neumann, we are not having yxn. Okay, so that's why we cannot use 4.7 to determine the value of S. So instead of using 4.7, so in order to use our second boundary condition, which is now we denote our y prime as the theta, okay, we want to use this y prime as n, so means that first you need to differentiate your
Fine.
y, okay? So you differentiate, you are getting y prime, u prime, remain as s, and v prime, s multiplied v prime. Why? Because s is just a constant. Okay, so y prime, u prime, v prime. So that's why you are getting equation 4.10. So since y prime, u prime, v prime, so we want to use the second boundary condition. So this second boundary condition, we are using particular x, which is x is equal to xn. So from your derivative just now, you plug in your x, substitute with xn. So now we have y prime Sn, u prime Sn, v prime Sn multiply s. So rearrange this one, okay, rearrange this one, and then you can get your s lah. So means that now s is equal to y prime Sn. What is our y prime Sn? Theta. That's why we are using theta. Okay. So this is u prime Sn. How can we get this u prime Sn? Okay, from IVP1. How about V prime Sn from IVP2? What is actually our U prime Sn? For example, U prime X4. You refer to our previous example. U prime X4 is actually Z X4 or Z4. Okay, previously. But in Dirichlet, we are not calculating Z4. Am I right?
Yes.
In Neumann, you need to finish that calculation until you are getting Z4 for IVP1. Okay, so similar to your IVP2, this V prime Xn is actually you can get from your IVP2. Now look at back your previous example for the Dirichlet. So IVP2 V prime basically is your W. Am I right? Because you let V prime equal to W. So means that okay, from this equation 4.11, this V prime is actually your W Xn. So if n is 4, means that is W x4 or simply W4. So previously in the Dirichlet case, this boundary condition, we are not calculating until W4. So now for Neumann boundary condition, you have to finish that calculation until W4, unless you cannot find S value. Okay, understand? Okay, so now once you get S value, okay, you substitute back to your S here, and then we use the same concept as what we did in our Dirichlet. Okay, just identify. Okay, sorry, you put I here, yxi, uxi, vxi. Now you have the value of S. Then you can find the solution of yi. So maybe I start from 1, 2, 3, 4. Then you substitute one by one. Then you get the solution y1, y2, y3, y4. That is your final solution. Just we use this y prime to determine S. That's it. When we are finding y, solution of y, we are not using prime anymore. Okay, we just use y here, usual y. Linear combination here. Okay, so that is actually your Neumann. Okay, how about if this is not y x naught? Okay, maybe we have another form of I didn't put it here. Where is it? Oh, I didn't put it here. Okay, so in the case of okay, let's say, okay, I stop this sharing, so I change to okay now. In the case of if you are having okay, let's say y okay, this is Neumann. Okay, in the case of let's say you're having y x prime plus x y plus x. So your condition should be y x naught equal to alpha just now, y prime x n is equal to theta. Okay, this is what we have in our lecture notes. So how about if okay, your condition okay y prime x naught. Okay, this is we are using if I'm not mistaken another symbol lah, maybe lambda. Yeah, lambda. Let's say lambda. Okay, and you are having this is okay xn. It's not prime. Okay, it's not prime. So maybe it's another gamma. So another value lah, another value. So if we have this case, okay, they are still for this linear second order, but different boundary condition. So this one I explained already just now, but now for this one y prime and also y. Okay, basically you have x naught until xn. Okay, for your x. So for this particular type of boundary condition, you need to use substitution. Okay, let's say use substitution. Okay, I'm using you may use any symbol lah. So just now you use so maybe you want to use normally what's kind of symbol? U X Y Z U V W X Y Z T S. Okay, I'm using S. Okay, S maybe. No, not S. S is your shooting. R is your. Yeah, let's say Z lah. Tak sangat kan. So maybe you can use any substitution Z equal to any other term here. But for example, I'm not sure whether this is fixed or not. Okay, the most important when we are using this example, this substitution, we will change. Okay, the objective is okay to change. Okay, to change. Okay, y prime not and y n into sorry no now z not and z prime. This is actually similar as just they are using z now because we use substitution z. Okay, so so then when you have this form, then you can use the same technique IVP1 IVP2 and use solution But for this one, maybe you are using Z equal to U plus S. Yeah, maybe V. But when you are solving U, do not use another symbol Z lah, because we use that here. So you get the solution. So then you substitute back lah. Okay. Substitute back, because Z is not our solution that we are looking for. We need Y. We need Y. We need Y. We need Y here. Okay. So this is the idea. The idea. So maybe I will give you that particular example later. So any question? Any question?
All okay.
Oh, maybe this is not. Sorry. I'll check this part. I'll check this part. Is it this is correct or not? I'll check this part. Because this Z is actually, we change the independent variable. We are not changing Z for Y. So this one should be not correct. Okay, this is not correct. Sorry. Because we are changing X. We are not changing Y. Okay. So maybe this is not Z naught. So maybe this is Y in term of X. Now we are getting Y in term of Z. Yeah, and then this is correct. Alright. So that is the theory for our Neumann boundary condition. We look at the example next week. Okay, on Tuesday. So is it possible if our next week meeting on Tuesday we make it 2 hours? Possible tak?
Tuesday.
Tuesday.
Yes, okay.
You have class at 11 Tuesday?
No.
No.
Yes.
Lepas tu Rabu cancel doktor.
Rabu tak adalah cancel.
2 jam ke?
Maksudnya
4 jam lah.
sekali jalan je 2 jam terus. So kalau kita
Boleh.
habis syllabus awal lepas tu kita buat latihan je lah.
Beres.
Boleh tak? Sebab macam
Boleh.
sejam-sejam je macam tak seronok pula lah. Rindu pula
Apa?
dengar suara saya.
Betul.
Boleh, doktor.
Kalau boleh nak muka sekali.
Oh, okey sekali. Sebab saya pakai yang tempoh hari saya pakai laptop. So laptop tu memang ada kamera lah. Yang ni saya pakai desktop tak ada kamera. Sebab tu tak appear kamera kat sini.
Tak apa. Dengar suara pun dah tahu dah.
Kan? Boleh ingat kan apa bayang-bayang
Boleh.
kan?
Muka, senyum.
Jangan terbayang-bayang sampai ke mimpi sudah lah.
Jangan, bahaya. Bahaya doktor kalau mimpi doktor.
Kan? Kau lain game. Kau memang takkan jumpa muka aku kat mimpi. Okay. So basically, that's the end of our session for today. Before we dismiss, maybe Zainab you can dismiss that, because I want to explain regarding